In the vast, arid expanse of Chile's Atacama Desert, a cosmic visitor has been discovered that defies our understanding of natural materials. Join us as we explore the Atacama Iron-Nickel Meteorite, a celestial relic with magnetic properties unlike anything found on Earth, and discover how this chance finding might revolutionize future technology while deepening our understanding of the cosmos. The Atacama Desert stretches across northern Chile, creating one of the driest, most inhospitable environments on our planet. With its reddish soil and barren terrain, scientists often compare it to the Martian landscape. It was in this otherworldly setting that the Atacama Iron-Nickel Meteorite, or AINM, was discovered, not by meteorite hunters, but by researchers studying extremophiles, those remarkable microorganisms that thrive in Earth's most challenging conditions. The expedition team wasn't looking for objects from space, they were focused on life forms that could survive in near impossible circumstances. Yet as they traversed the desert floor, something unusual caught their attention, a rock that seemed oddly heavy for its size, with a distinctive metallic sheen that stood out against the rusty terrain. This chance encounter would lead to one of the most significant meteorite discoveries in recent years. Upon closer examination, the research team realized they had stumbled upon something extraordinary. The unusual weight and metallic luster of the rock weren't its only distinguishing features. Initial field tests suggested it wasn't of terrestrial origin at all. The object was carefully extracted and transported to specialized laboratories for comprehensive analysis. There, scientists confirmed what they had suspected: this was indeed a meteorite, a fragment that had survived the violent journey through Earth's atmosphere after breaking away from its parent body somewhere in space. Dating techniques and compositional analysis revealed clues about its cosmic journey. The meteorite likely originated from the asteroid belt between Mars and Jupiter, where catastrophic collisions between larger bodies created fragments that were eventually pulled into Earth's gravitational field. The AINM represents a tangible connection to the distant reaches of our solar system, a messenger carrying information about conditions and materials that exist far beyond our planet. What truly sets the Atacama Iron-Nickel Meteorite apart is its remarkable internal composition. While iron-nickel meteorites aren't uncommon, the AINM exhibits crystallographic patterns unlike any previously documented specimens. Advanced spectroscopic analysis revealed the unique arrangement of iron and nickel atoms that suggests formation under conditions dramatically different from those on Earth. When researchers examined thin slices of the meteorite under powerful electron microscopes, they observed distinctive Widmanstätten patterns, intersecting bands of nickel-iron alloys that form only during extremely slow cooling over millions of years. However, the AINM's patterns displayed unusual angles and spacing, indicating it may have experienced different pressure conditions or chemical environments during formation. These structural anomalies provide valuable insights into the diverse conditions that existed in our early solar system, potentially revealing details about planetary formation processes that we cannot directly observe today. Perhaps the most intriguing aspect of the AINM is its extraordinary magnetic behavior. Typical ferromagnetic materials like standard iron or nickel become magnetized when exposed to external magnetic fields, but the iron-nickel alloy within this meteorite exhibits intrinsic permanent magnetism without prior exposure, a phenomenon rarely observed in naturally occurring compounds. When researchers tested the meteorite's magnetic properties, they found it generated magnetic fields significantly stronger than terrestrial iron-nickel compounds of similar composition. Even more puzzling, these magnetic properties remained stable across a wide temperature range, defying conventional understanding of how such materials should behave. Some sections of the meteorite displayed localized magnetic domains with polarities oriented in patterns that seem to preserve information about the magnetic environment of its formation. This exceptional magnetic signature has become the subject of intense study, as it may hold clues about magnetic field conditions in the early solar system or even the magnetic properties of the parent body from which the meteorite originated. How did the AINM develop such unusual properties? Scientists have proposed several theories about the extreme conditions that might have created this anomalous material. One hypothesis suggests it formed in cooling nebulae during the early stages of our solar system, where unique combinations of temperature gradients, radiation exposure, and chemical environments could have produced novel crystalline structures. Another theory points to the meteorite originating from the core mantle boundary of a differentiated planetesimal, a small planetary body that formed early in our solar system's history but was later destroyed in a collision. At this boundary, Extreme pressures and temperatures, combined with the presence of other elements, might have created the perfect conditions for forming these unique magnetic alloys. These formation scenarios represent processes that cannot be replicated in laboratories on Earth, making the meteorite an invaluable window into cosmic phenomena that would otherwise remain theoretical. By studying the AINM, researchers are essentially conducting experiments that would be impossible to perform on Earth, gaining insights into the extreme physics of planetary formation. The discovery of the Atacama Iron-Nickel Meteorite has sparked collaboration across multiple scientific disciplines. Geologists study its mineral composition to understand the processes that formed it. Astronomers use it to test theories about conditions in the early solar system. Material scientists examine its unique structure for insights into novel alloy formations. Physicists probe its magnetic properties to better understand fundamental forces. This cross-disciplinary approach has created a rich research ecosystem around a single specimen. Research teams from universities across the globe have requested samples for analysis, while space agencies have shown interest in how the meteorite's properties might inform future missions to asteroid belts or other planetary bodies. The AINM has become a nexus for scientific collaboration, demonstrating how a single discovery can bridge traditionally separate fields of study and create new avenues for research that wouldn't exist within the confines of individual disciplines. Beyond pure scientific curiosity, the unique properties of the AINM hold tremendous potential for technological applications. Materials exhibiting inherent magnetic characteristics under novel conditions could revolutionize numerous fields. In electronics, alloys inspired by the meteorite's composition might lead to more efficient components that generate less heat and consume less power. Data storage technology could benefit from materials with stable magnetic properties, potentially increasing storage density while reducing energy requirements. Medical imaging might advance through improved MRI machines utilizing novel magnetic materials that produce clearer images at lower magnetic field strengths. Even energy production could be transformed through more efficient generators and motors based on these unique magnetic properties. Engineers and materials scientists are already attempting to synthesize analogs of the meteorite's composition, hoping to recreate its properties in laboratory settings. While perfectly replicating cosmic conditions remains challenging, even approximations of the meteorite's structure could lead to significant technological breakthroughs that transform everyday devices and specialized equipment alike. Despite its promising properties, studying and potentially replicating the AINM presents significant challenges. The meteorite's formation occurred under conditions impossible to fully recreate on Earth: extreme pressures, near-vacuum environments, and cooling periods spanning millions of years. Laboratory attempts to synthesize similar materials must use innovative approaches to approximate these conditions. Researchers have experimented with rapid quenching techniques, high-pressure chambers, and even microgravity environments on space stations to create analogs with similar properties. Additionally, the meteorite's age presents analytical challenges, as billions of years of cosmic radiation and subsequent terrestrial exposure have altered some of its original characteristics. Scientists must carefully distinguish between primary features formed during the meteorite's creation and secondary features resulting from its long journey through space and time on Earth. These challenges have pushed the boundaries of materials science and analytical techniques, driving innovation in research methodologies even as the meteorite itself continues to resist full characterization. Given the scientific significance of the Atacama Iron-Nickel Meteorite, careful preservation has become a priority. The main mass of the meteorite is now housed in a specially designed facility that protects it from oxidation, humidity, and temperature fluctuations that could alter its properties. Small samples have been distributed to research institutions worldwide, but with strict protocols to ensure minimal destructive testing. A digital three-dimensional model of the meteorite has been created through advanced scanning techniques, preserving its structure virtually for future generations of scientists. Long-term research programs have been established to study the AINM over decades, recognizing that as analytical technologies advance, new properties may be discovered that current instruments cannot detect. This approach to preservation balances the need for current scientific inquiry with the understanding that future researchers, equipped with technologies we cannot yet imagine, may extract even more knowledge from this cosmic visitor. The meteorite has become not just a scientific specimen but a carefully managed resource for ongoing discovery. The Atacama Iron-Nickel Meteorite represents just one sample from the vast cosmic laboratory of our solar system. Its unique properties raise intriguing questions. Are there other meteorites with similar or even more exotic characteristics still waiting to be discovered? Might these materials exist in abundance on certain asteroids, potentially becoming valuable resources for future space exploration and off-world manufacturing? The AINM has prompted space agencies to reconsider the potential value of asteroid mining beyond precious metals, looking at novel alloys with properties that could be crucial for advanced technologies. It has also inspired new detection methods for locating similar meteorites in other extreme environments on Earth. The deserts of Antarctica, Australia, and the Middle East are now being surveyed with instruments calibrated to detect the specific magnetic signature of AINM-like materials. As our understanding of this remarkable meteorite grows, it continues to expand our cosmic perspective, reminding us that the universe contains materials and phenomena far beyond what we typically encounter on our home planet. The Atacama Iron-Nickel Meteorite stands as a testament to the extraordinary diversity of materials that exist beyond our planet. From its chance discovery in one of Earth's most extreme environments to its unprecedented magnetic properties that defy conventional understanding, this cosmic visitor continues to challenge and expand our scientific knowledge. The unique crystallographic patterns and magnetic behaviors observed in the AINM offer us glimpses into conditions that existed during the formation of our solar system, conditions impossible to recreate in terrestrial laboratories. As researchers from geology, astronomy, physics, and materials science collaborate to unravel its mysteries, the meteorite serves as a catalyst for cross-disciplinary innovation. The technological implications of understanding and potentially replicating its properties could transform fields ranging from electronics and data storage to medical imaging and energy production. Though the challenges of analysis and synthesis remain significant, the ongoing study of this remarkable specimen promises to yield insights for generations to come. In the story of the Atacama Iron-Nickel Meteorite, we find a powerful reminder that our universe still holds countless secrets waiting to be discovered, and that sometimes, the most significant scientific breakthroughs begin with simply noticing something unusual in an unexpected place. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.